essentially, we wrote down the Lofting wave function. And as I stressed in the last lecture, it's not the right answer for the Coulomb repulsion. It's a very good approximation to it for a small number of electrons. But what's important is that it lies in the right universality class, in a way that we'll see in this lecture. So it really captures the right physics of the true gravity. So what I want to do is in the second half of the lecture, is start to explain what that physics is. In the first half, I'm going to tell you about something called the plasma analogy. And the point is the following. This is a very easy wave function to write down. It's a wave function for a large number of particles, but it's very short when you write it on the page. But if you want to compute anything using this, you have to compute an expectation value, because it's quantum mechanics. And an expectation value means you take an operator and you sandwich the wave function on either side, and then it's old-fashioned quantum mechanics where you don't just get to write that, you actually have to do the overlap integral. And then you have to integrate over all of these degrees of freedom. And there's a large number of degrees of freedom. And this becomes an extremely hard thing to calculate. You just can't do the integral. So Lofting cooked up a very nice trick called the plasma analogy that for certain coarse grain variables just allows you to do these integrals. Doing them is maybe an exaggeration. It allows you to guess what the answer is.
I thought another trick that one services felt is that it's almost like it's later determinant. So, some kind of a many-body understanding of this would be great.
N equals 1, it is a Slater determinant. It's the M that makes...
With any odd M, it's not, I see.
No, it's a Slater determinant N equals 1. And you can see that because N equals 1 is a fully formed lambda length. So it's really just the determinant of all the lambda lengths. But it's not for M. Okay, so it's called the plasma analogy. Lofting was actually trained in understanding stat mecha of 2D plasmas. So it's kind of remarkable that all of that knowledge, which should have nothing to do with the quantum world effect, just turned out to be useful. So here's an example of something we'd love to compute, and as we'll see, it's hard. So let's compute the average density. Before we compute anything, let's just look at the wave function. Think about what the average density is. So this is a wave function for a lot of particles. And you can see that if they move too far from the origin, the wave function gets exponentially suppressed. So you expect these wave functions to be confined to some distance near the origin. But you can also see that there's this factor here, which is growing when the particles move apart. So the very, very basic question is, what's the average density this is? And it's not clear. My intuition would be that the density is maybe peaking something in the origin and drops off because it looks like this is winning, but then I'm not really taking into account this. And this is very complicated, right? Because it's got 0 whenever they come close together. So it's not obvious just staring at this what kind of object we're describing. It's a disk. The way the density varies over the disk is not clear. So what we're going to do is just try and calculate. So the way you calculate is you introduce a density observable that depends on Z, the position, and it's just the obvious thing. It's the sum of all the particles with a delta function peaked at that particle, and you might hope that as n gets large, you can have the expectation value of this as some nice smooth function. So what is the expectation value? It's the expectation value. The density at position Z is, of course, the Lofting wave function. The operator sandwiched between the Lofting wave function, which I'm going to write in the following way. To n. So we have to do these large number of integrals, which are all going to be hard. N of Z, and then here is the modulus squared of the Lofting wave function, which I'll just write as this. And this thing that I've called capital P is just the mod square of the Lofton wave function. In fact, I'm just going to add a normalization factor so that P is dimensionless, but this normalization factor just cancels out on the top and bottom. Okay, so this is, the Lofton wave function wasn't normalized, which is why I've got it on. Okay, any questions? Alright, so if you want to work out the density of this Lofton state, these are the integrals that you have to do. And
there's something that may I just ask? When we say I less than j, we just order. So I are the levels of particle, but we just order them in some way.
Let's do that. Yeah.
Because if since m is not even, it matters in terms of phasor at least.
That's right. M not being even just makes this anti-symmetric.
It makes it anti-symmetric. Yeah, that's right. Okay. So, but we need to order in some way. Right?
I mean, it really just means summing over pairs.
Some over pairs, but
and there's a minus sign. That's right. It's a minus sign depending on the order.
So you're saying
fermion exchange lines.
So you're saying each pair is taken once and exactly once.
Exactly.
And it doesn't matter which way you take the pair because that's an overall sign in the sign.
It's an overall. But of course,
if I take the sign.
It matters in this. Well, I fix some ordering. I compute the wave function. Then
yes,
there's an overall sign.
Afterwards, but once and for all, you.
Yeah, but you have to fix some ordering.
Once and for all.
Yeah, once and for all.
Okay, so any more questions? All right, so very basic question, like what's the density of the Lofton state? These are the horrible integrals that you have to do. And of course, there's no way to do these integrals. However, they look like the kind of integrals that we can't do in another context. They look very much like the kind of integrals that arise in classical statistical mechanics. So it's the kind of thing.
Coulomb gas, right?
Yeah, exactly.
Coulomb gas. Including
kind of thing that arises. And we know that the conformal field theory approach to the Coulomb gas is really just the view from the edge. That's the heart of it. So it's the kind of thing that arises in classical static. Okay, so let's just make that very, very clear by just giving new names to everything that's here. I'm going to write P of Z to be e to the minus beta ui. Okay, so this is the definition of beta times ui, where beta ui is minus 2m times the log, times the sum of I is less than a, the log of mod z minus mod j is b plus 1 over 2 b squared dx. Okay, for those of you that come in, we're doing a very simple calculation. We're just calculating the density of particles in the Lofton state. This is the Lofton state, this is the density operator, and we're just computing the expectation value of this density operator in the Lofton state. And what we're finding is you have to do some horrible integrals that we can't do.
Why is this going to plasma energy?
We'll see shortly. So it's a trick for doing these calculations. In general, it's a trick for computing the expectation values of things in the Lofton state. So these are the integrals where P is defined by the things there, and then I've just rewritten P as e to the minus beta something. All right, so Sandeep and Gautam were already ahead of us. The key idea is the following. Okay, we've written this as e to the minus beta times u, and the thing that sits on the bottom, at least, it looks very much like the partition function for the classical static problem if you integrate over everything. So the key idea is to try and find some system that we're familiar with that has this as its energy. So we'll try and interpret this as a static problem. And then to use our intuition about that static problem to think about what the answer is likely to be. Okay, so it turns out, and I'll show this, that the interpretation is clear if you take a very specific value of beta. So there's a clear interpretation. If beta takes the value 2 over n. Okay. So why is that? Well, if I put beta equals 2 over n, this potential is this. Okay, so there's factors of 2 that just work themselves out. The key thing of taking beta to be this is that there's an m squared here relative to an n here.
Wait, I'm sorry, but you define beta u to be whatever we got by writing.
That's right, yeah, but I didn't define beta and u independently.
Okay.
So now I'm saying that u has a very nice interpretation if you take beta to be this specific value.
Okay.
This will be important.
What is the interpretation of
What's the interpretation of u?
No, you said you have a nice interpretation.
Yes.
Oh, you're writing
I'm going to write it down. Okay, so what's the interpretation of u? Let me tell you in words. The interpretation is that and I'll show this now, that this is going to be a gas of particles in 2 dimensions, moving around and interacting through a Coulomb force in 2 dimensions. And then we'll see why this is. So this is the energy of a 2D plasma. Particles charge, and I'm going to put charge in inverted commas, q equals minus n. Okay. So the charge is in inverted commas because this charge has nothing to do with the charge of the electrons. Okay. This is an entirely auxiliary construct that we're just cooking up. It's completely fake plasma. There's no real plasma here. It's just a way to try and compute the expectation value of operators that are not here. All right. So why is this statement true? Okay. So it's a 2D plasma. This means in particular that the particles are moving in 2 dimensions, but they're experiencing Coulomb forces that arise from 2-dimensional Maxwell fields, not real Maxwell fields. So let's look at this. There's 2 terms. And let's look at the first term first. So in 2D, Gauss's law so phi is the electrostatic potential, but it's going to be an electrostatic potential just in 2 dimensions. So what have I done here? I put a particle of charge q at the origin, and I solve for the electrostatic potential. This is Gauss's law. This is Gauss's law in any number of dimensions, just 2. But if I solve it in 2 dimensions, meaning this is a 2D Laplacian, not a 3D Laplacian, then the solution is a log, as opposed to a 1 over r in our case. Which means that this is the electrostatic potential for a particle of charge q. The energy of 2 particles, both of charge q, is just going to be q squared times log. That's exactly what we have here. Q is n. So what we've got here is the electrostatic energy summing over pairs of particles, where each particle has charge.
So LB is some short distance cutoff in that?
LB is just, I said it's a long distance.
Oh, it's just a boundary.
It's just a constant term that I've picked, but it's arbitrary, right? I've just chosen it to be.
I see. So, well, I was asking whether it regulates the short distance behavior or the.
It's not the size of the system, right? It's not.
No, it's not the size of the system, but it's just a constant.
It's just the.
Okay.
You just think of it as the integration constant.
It's the short distance.
Okay, term 2. Term 2 is slightly more subtle, but the way to think about it is the following. So, suppose that this was the potential energy coming from some electrostatic object. So, if it was, then you could put it back into Gauss's law and ask what kind of charge distribution would give rise to it. So if you act with a Laplacian on mod z squared, you differentiate z, then you differentiate z bar, and you just get a constant. So what this is telling us is that there's also this constant background charge in the system. So this is really a plasma of particles moving around, Coulomb forces between themselves, but this term is all the particles interacting with some constant background charge. Each particle experiences constant background charge, which, if you put all the numbers in, turns out to be 2 pi is just 2 pi. Okay, so is that clear? We're just trying to compute expectation values in the Loftin state, and the problem we end up with is a stat-mech problem of figuring out the partition function for a 2-dimensional plasma, where there's a bunch of particles in a background charge. So what's going to happen? We don't have to be experts in plasma physics just to guess the answer. There's some constant background charge, and the equilibrium situation is going to be so that where the particles maneuver themselves in such a way that on average the charge is neutral. So the background charge has one sign, the particles have the opposite sign, so you just expect them to arrange themselves with a density such that it cancels out this background charge. Okay. So we expect particles to equilibrate at neutrality. Yeah, please.
The background charge is negative and the charges themselves are negative, right?
Then I've got a minus sign. Minus signs are not guaranteed, but they're the opposite. You could see it because I think the terms in the potential.
Yeah.
Okay, so what does neutrality mean? Neutrality means that n, which is the density of particles, this is the object we were starting with, times m, which is the charge of this fake charge in the plasma, is equal to the background density, which is rho 0. Which tells us that n is equal to 1 over m and 1 over 2 pi delta squared. So this is exactly the density that we would need for the Loftin state. Meaning the density that we would need for filling fraction 1 over n. But without doing any calculations, it told us the answer to the original question. Remember, the original question was, if you look at the Loftin wave function, we know it's some disk of finite radius, but it's not at all clear how the density varies. Remember that? It's bigger in the middle or bigger at the edge. This tells us the answer. It's just constant. It's constant everywhere throughout the disk until you get to edge effects that we can look right at. So it is constant throughout the whole space. Okay, so it's a very clever argument because it's not at all obvious that this is true.
But
Yeah, okay.
isn't this going to only work if your temperature, which is 2 over m, is in the low temperature phase of this plasma?
Good. So let me. I'm going to comment on this next. But so far, what I've said is true regardless.
Well, you said that at low, I mean, you're finding how you will minimize the entropy. There's no entropy effect in the cooler here. So if I'm at high temperature, presumably if I'm at high temperature, you can pay some energy cost and gain some entropy by not being in this ideal charge distribution or no?
So what are the two likely options as you vary? Actually, it's varying temperature and density. It's a little bit awkward because temperature goes as 1 over m and density goes as 1 over m, so low and high aren't quite as clear. But roughly the two phases you expect are a solid or a liquid.
Right. So you might make a solid if
but both solids and liquids on large
average.
So what I've said here is true regardless of the phase of the plasma.
Okay.
You would need some horribly inhomogeneous phase for this not to be true, but I'm no expert in plasmas, but that seems very unlikely.
Okay.
Sorry, so you're saying whether it's a solid or liquid on large enough scales, the charge will organize itself to cancel the background.
Okay, yeah, that's fact.
Yeah. But then now this becomes important. If you want to ask more detailed questions about the density of particles in a Loftin state, you need to know what's the phase of this object. Is this Spatnik problem a liquid in this regime of parameters? That was this. So beta we had to set at the beginning to be.
So in this formula, n should be interpreted as the average charge. And on average, it's a constant.
That's right. Yes, exactly.
Not ruling out other.
Absolutely.
Not the correlations.
Yeah.
So there's something more basic which is what the mapping of the problem to plasmas told us was what beta U is, right? And then we cooked up a beta which gave us a physical interpretation.
That's right. Yes.
Yeah.
Aren't we allowed to do that? I mean, that is.
You could use a different beta, but then you need to come up with a new interpretation for the U.
Right.
So this was a beta that had a nice interpretation.
Right. But since beta was up to us, we cook up a beta which allows us to get a physical map of the problem.
But I don't think there's a natural interpretation for any U other than this.
Correct. So let's choose this beta.
Exactly. Yeah.
And the answer shouldn't. This is just convenient to be able to map the problem to physics.
But now we have a question. We fixed beta and we fixed the average particle density.
What's the phase?
So now there's a question, what is the phase of this plasma? Does it form a solid or does it form a liquid?
Okay.
Which is a more subtle question about how the correlations between the electrons
Yes,
are.
I got it. Right. Quite true. Okay, I understand.
And so for this
Fair correlations, not just average.
Exactly.
Right, yeah. So this is just fixing the average.
This is fixing the average.
So that there's no global Coulomb energy cost.
Exactly. So now we have to answer this question if we want more detailed knowledge. And there's no easy way to answer this. What you have to do is open up plasma papers or doing numerical simulations to find out where the phase transition happens between the solid phase and...
Can I ask something?
Yeah.
If n goes to infinity, so that the temperature goes to infinity, the plasma also the density also seems to become very diluted.
Exactly. Right.
So that's a phase where we should be able to say something, right? Isn't it a very dilute, very high temperatures, a bunch of basically very weakly interacting charges, no?
In this background. So let me tell you the answer and then we'll come back to this, because the answer is a little bit counterintuitive. So numerically shows
Large and beta is going to 0 now. So temperature very large.
Just to get an idea, why is that question important? Whether it's in a solid phase or in a...
So at the moment it's going to be important for just some stupid detailed question about exactly what the correlations between electrons are in Loftin space.
It's very important, right?
But later in this lecture it's going to be crucial when we come to another calculation.
No, for example, if it turned out to be a solid, you would say you found a crystalline phase of electrons, not a fluid phase. The quantum Mott droplet would be a crystal.
Oh, I see. You think that the conductivity...
If for some m you found that the plasma is in a solid phase, then the electron droplet has developed as it's a solid. Right? It would be a Wigner crystal or something.
You know, so this is a subtle issue. So I should tell people the background. One of the reasons this was surprising is that people thought that you wouldn't form a Hall, meaning this being the whole discovery of the fractional quantum Hall effect. People thought you wouldn't form a quantum Hall fluid, that you would just form a crystal. And the crystals are called Wigner crystals, and they're basically just electrons localized on the points of a lattice due to the Coulomb repulsion between them. And there's a wave function you can write down for the Wigner crystal, and there's the Laughlin wave function. And you have to compare the two to see which energetically wins, and it turns out the Laughlin wave function wins. Okay. That's a different calculation from the one we're doing.
Yeah, but it could turn out that the Laughlin wave function itself for some M is a crystal.
Exactly.
Right.
So let me just tell you the answer, and then we can come back and discuss this. So the answer is the following. The numeric shows that we have a liquid as opposed to a solid. If M is less than around 70. Okay. Which means that for all the Laughlin states we're interested in, M equals 3, M equals 5, we're clearly in the plasma phase, not in the solid phase, and that this Laughlin wave function is describing correlations between objects that are like a liquid rather than like a solid.
Can I ask you
Yeah.
a very dumb question just to reveal my total ignorance? In 2D you can get solids. I mean, don't you have the long range?
That's true. Does the magnetic fields help?
Okay.
Yeah, I did. Right, the mermaid being the.
Right.
I think the mermaid.
Right.
Whoever this guy's are.
Right. Exactly. Right.
Mermaid Magnus. Right. This is something else. I think there was a solid. That's right. Mermaid Magnus is moving. Right.
But then.
The translations are a continuous symmetry, and then
Well, there is the analog of Kostelis-Thouless theory, right, for solids in two-dimension.
Yeah.
So you can have, just like your superfluidity in a thin two-dimensional film, although Momin-Wagner's theorem says no symmetry, so you can have stiffness without symmetry. So it's a power law solid.
Is there still a valid for Coulomb interaction?
That part I don't know, but I'm just saying.
It doesn't work for Coulomb interaction. Long range interactions, Marvin Wagner has to carry out short range interaction.
Marvin Wagner doesn't work for long range. Because it's more a statement that the kinetic energy is always a log effect.
Yeah, you are
the potential.
Exactly. That breaks down if you have.
I see.
No. But
now the kinetic energy vanishes. So I'm not sure. I think the magnetic field might be.
Okay, for example, Marvin Wagner uses things like CK modes and so on.
Yeah.
You have long range, you think you're sitting at plasma.
Yeah. But even if that wasn't the case.
Hey, how you doing?
All right, cheers.
Carl, this is everybody. Everybody, this is Carl.
I see.
Here's something that I find a little counterintuitive. I think it's related to Sandeep's question. Let's go to very high temperatures. Very high temperatures and very low densities is M very large, but M large is where you form the solid. And you would imagine that you form a liquid at high temperature. But I think the point is that you form a liquid at high temperatures keeping this density fixed.
Yeah.
And so at very low densities and keeping the temperature fixed, you actually expect to form a solid.
Yeah.
Because that's where
Coulomb repulsion.
where Coulomb repulsion is supposed to work. Coulomb repulsion as opposed to there's no kinetic energy. Yeah, that's exactly the fact that
entropy must be
entropy. Yeah, as opposed to entropy. It must be that. Yeah, as opposed to entropy. Yeah. So it's a little counterintuitive, but it's because you don't get to vary temperature and density independently. You only get to vary this. Yes.
In the wave function, there is a zeta minus zeta to the power m and the exponential minus z square.
That's right.
And looks like for certain values of m, the exponential can win, and certain values of m, the exponential will lose out. Repulsion.
No, L squared is dimensionful, and m is just a dimensionless number, so they can't sort of compete against each other.
No, I mean the exponential will. The things clumping together is prevented by the zeta minus zeta thing.
That's right. That's right. Yes.
And the things clumping at the origin is, favored by the e to the power.
That's right.
Shouldn't there be competition depending on what power you put in zeta minus zeta to the power? I mean, if it clumps together or
that's determining the size of the disk. Ultimately, remember the size of the disk goes as a square root of m. The area of the disk goes as m. So I think that's it. To understand, I don't know how to understand this phase transition in terms of. But it's there, so maybe you're right.
I don't know. There should be. It looks like there should be a competition between the exponential and the power law.
So that's clearly happening. The exponential is trying to squash everything to the origin. The prefactor is trying to.
So we need a solution where it always bears out to be a uniform thing.
So it's always uniform. That's the remarkable thing. Is that if you just compute the density of the Loveling wave function, it is uniform.
For any end.
For any end. Yeah. That's what we showed here because that's what we showed at this stage. Not if you look on short distance scales necessarily, but on any distance scale, it's very surprising. It's not obvious. But
one more comment. This question of whether a charged particle crystal exists in 2D. The usual answer has to do with the fact that you have the particles living in 2 dimensions, but their electric field lines live in 3 dimensions. And that's the case in which we know that the defects don't interact logarithmically, and therefore you can't have this 2D thing. Now here these charges have field lines also living in a dimension. So I don't know what happens actually.
No, but Mermin-Wagner theorem is a theorem that applies just to 2D fields.
No.
This is a 2D.
So we are going beyond Mermin-Wagner and saying what kind of long-range interactions causes what kind of problems.
Oh, but it's worse in 2 dimensions then, right?
No, we are in 2 dimensions.
Yeah, exactly. But long range is worse in 2D.
No, but the question is what kind of long range. So when people usually say a charged particle system in 2 dimensions can not have this power law phase, they mean that you have electric field lines that go in all 3 dimensions. The charges live in 2 dimensions.
No, but Kedar, what he's saying is that potential is 1 over r.
Yes.
This is log r. It's even worse.
Yeah.
In that argument, it's even worse.
It's IR divergences that give rise to this Mermin-Wagner theorem.
So you would want to know what's the interaction between the defects, not between the charges.
Between the vortices.
Between the vortices in the solid order parameter. That's the one that you have to ask. Is it logarithmic or not? If it's logarithmic, there's a continuous solution, otherwise not. So I don't know.
Yeah.
In the charge particle argument, you say that the vortices in the guy don't interact logarithmically anymore because there are screening currents that screen out that. And that relies on the electric field being in 3 dimensions.
The question's a little bit moot though, because there's
Yeah,
a question about what's the phase transition between liquid and solid
yes.
phase and is it Costello Dallas? And we're just never going to get
So I guess I'm just wondering what are the interactions between the defects when the charges are actually truly 2D electric.
What are the defects?
I mean, so you make a solid structure, and then the defects are sort of the crystal defects. Yeah. Those are the analogs of vortices, right? So that I don't know.
All right. So that's where we are. The fact that it's a liquid and not a solid is going to be very important for our next conversation. All right. Any questions about plasmas before we move on? So next thing I want to tell you about is quasi-poles and quasi-particles. Which is not now a statement about the Loveling wave function, but a statement about the excitations above a Loveling wave function. Alright, so let's start with a quasi-pole. Quasi-pole excitation. And I'm just going to give you the wave function that describes a quasi-pole. Okay, so I'm sort of following in this tradition of just making stuff up, right? That's what we're doing in the fractional quantum Hall effect. We made up a wave function for the ground state. We just guess. We've done exactly the same thing here. We just guessed a wave function for the first excited state. At some point, this kind of seems to get a bit silly to me. You just keep guessing random wave functions. It turns out that firstly, it's a very simple wave function. That's one of the things that's got going for it. If you want to do things a little more systematically, you you can do the following, and it's in the notes, although I'm not going to write it up here. You can construct a Hamiltonian for which the Laughlin wave function is the unique ground state. And you do it in reverse. You look at the properties of the Laughlin wave function, you see what Hamiltonian can I write just where that happens. It's quite easy to do. And then in that Hamiltonian, you can ask what are the excited states. And it turns out that this is the excited state. So you can give some kind of justification.
Sorry, so eta is the coordinate of the...
Good. So eta is going to be the position of the quasi-hole. It's a complex number. It's the position of the hole. And you can see, so the z's are the dynamical variables, but eta is just a parameter that we fix. It's not something dynamical. It's going to be the position of the hole. And you can see what it does. The electrons don't want to go near eta because the wave function vanishes if any of the z ions is. So what it's doing is carving out a little region of space in the neighborhood of eta where no electrons will go, which is why it's a hole instead of a particle. Okay, it's a deficit of charge in that region because the electrons get pushed.
So the size of that region is LB?
The size of that region, everything is LB, yes. All right, so this state has a couple of remarkable properties, and the purpose of the rest of this lecture is to prove them. Let me just firstly, yes, please.
I'm still very confused. I thought that you had, let's say you had whatever, n electrons to first have the Laughlin fractional 1/m state or whatever. And then you were interested in the wave function, and for that state you had the Laughlin wave function. Then you're interested in taking one electron out of the system and describing the resulting wave function. Is that right?
No. We've got the same number of electrons. Okay. The n that you started with forms this disk. And what we're doing is writing down the wave function where in this part of the disk, the wave functions are all the electrons are all pushed away a little bit. So there's a deficit. The boundary of the disk is going to have to swell a little bit to compensate for that. So this describes the same number of electrons, a slightly bigger disk.
So it's a real physical hole, not a hole in the sense of electron hole theory or whatever, where in metals or
it's
something.
very similar to hole theory in the sense that you've just you've carved out that region of space. What do you do in hole theory? You have momentum. You fill up things in momentum space, and you carve out something from the momentum space. But in the lowest Landau level, momentum and position are basically the same things. So I think you should think of it in the same way as holes in math.
This is one particle excitation in the sense it has one charge less. That's what I get.
No, it doesn't have that.
That's the point.
So what?
It's like a density acceleration essentially.
No, but you increase the area, right? So if I kept the area fixed, I could reduce the number of particles by 1.
No, not to get this state. So this state has two striking and remarkable features. The first of which I'll write down, and we'll see why it is. So the first claim is that the charge of this state called E star, and remember the electron had charge minus E. This has charge plus because it's a whole number electron, E over N. So this is an object which doesn't carry the charge of the electron, but carries a fractional charge of the electron. It's very striking.
Sorry, I just want to understand that you do have n electron. This charge is defined how?
Yeah.
We're going to define it more rigorously in about 10 minutes.
I mean, but the system does have n electrons to begin with. And,
yeah. So the idea is that I can write down the wave functions for more holes just by giving this some coordinate eta 1 and keep multiplying by these same factors. Then multiply by another factor with eta 2 and another factor with eta 3. And the claim is that in this system, these are the objects which can independently move around. So that really the dynamical degrees of freedom that's moving around in this quantum Hall fluid have charge E of n. And it's been measured. It's been measured experimentally in very convincing experiments. Certainly in the m equals 3, when you use the third state, you can measure this charge.
You have anti-symmetries over the whole positions in that case?
No, so at the moment these are just, these are not dynamical degrees of freedom.
But suppose you have eta 1 and eta 2.
Yeah, no, you just multiply the two together in the wave function. The question about their statistics as they move is exactly what we're going to talk about in the next lecture. Okay, so let me just give some heuristic argument for this, and then we'll prove it Sure. So heuristic argument. And the argument is just consider m quasi-holes in the same location. So all at position eta. Then the wave function for m quasi-holes, you just multiply m. You just put m factors of this in the wave function. But now you can see that the way the quasi-holders appear is on exactly the same footing as the way the electrons appear. So if this was the position of an electron, this would simply be the wave function up to extreme normalization here of n plus 1 electrons. But it's not a dynamical degree of freedom for an electron. Instead, eta is just a parameter, and this is an absence of charge, not an excess of charge in this region. So this should be, because this looks the same as an electron, this should be a deficit of charge equal to the electron charge. So this should have charge E as opposed to minus E. Which means this should have charge 0.
The factor of e to the minus mod eta square,
because this is a parameter, I can just put it in. It's just a normalization.
And just to understand, David, so I suppose the point is that the Hamiltonian, which has the Laughlin wave function as an approximate good ground state, also has this, the whole psi hole, as an approximate good, say, first excited state.
And I think numerically you can show that that's true. Okay, so the argument is this looks just like an electron, meaning this term looks just like this term, except it's the absence of an electron. Okay, so the charge of this should be E, which means this is just M of these, so the charge of this should be E of M. Like I said, we'll see a much more sophisticated argument very shortly.
Does the plasma analogy suggest?
It's in the printed notes, and we'll see it kind of in passing in about 15 minutes' time. But this just looks like an impurity in the plasma analogy. If you take the wave function I've just rubbed out and write it as a plasma analogy, eta looks like an impurity. What's the charge of the impurity? Well, it's exactly 1/n of the charge of the electron. So, okay, what about a quasi-particle? So a quasi-particle has charge E star is minus E over m. And these quasi-particles turn out to be a little bit harder to write down than the quasi-holes. So we're going to write it down here, but as you get to more complicated quantum Hall states, I don't think people even have expressions for these quasi-particle wave functions. So let me explain why it's a little harder to write down. So let's go back to the single quasi-hole. We'll set m equals to 1 here. And let's put the quasi-hole at the origin. Okay, so eta is 0. The way you get a quasi-hole is just by multiplying by 1 power of z for every particle. Okay? So what does that do? It takes the angular momentum of every particle and moves the angular momentum, increases the angular momentum by 1, which pushes the particles away from the origin. That's what we've seen in single particle wave functions. So what we want to do to get a quasi-particle is have an excess of electrons in some region. And the way to do that would be to decrease the angular momentum of every particle by 1 in that region. But that's tricky, because the obvious ways to do it, well, you could try and divide by products of these. That's not going to work because you're going to get some singular wave. Or you can multiply by z bar. That's an obvious way to decrease the angular momentum, but that's not a wave function in the lowest Landau. So it's a little bit tricky to write down wave functions which increase the density of electrons. The way you do it, it turns out, is you differentiate with respect to z. Okay, that's a way of knocking off A from this part of the wave function. So the wave function is side particle, and the bit you differentiate is only the free factor, you don't differentiate the exponential. This is the quasi-particle wave function. The factor of 2 is annoying. When I was writing this, I figured out where it came from, but I forgot it. Does anyone know? We'll see these kind of things later when we talk about Jane wave functions. I have a feeling that I explained the factor of 2 there. So the factor of 2 is a little bit subtle.
Is it not a metric, the fact that dz, z bar will...
No, dz is described, but yeah, it's not that factor of 2. Dz has a factor of half in.
What is eta I?
Eta I is the position. But it's written as a barred object, because this is like 1 over there.
But there should be an I on it, or no?
Sorry, no. Sorry, thank you. Alright, so in this case we have wave functions, but it turns out because there's a derivative in here, they're much harder to work with than the quasi-particle. So everything we'll do is in terms of quasi-holds. And as I said, in the literature, people only ever work with quasi-holds, and I think don't even know what the quasi-particle wave functions are for more complicated space. Okay.
But again, to the extent we trust this, ultimately it's all sort of backed up by numerics. That's why we...
Up to the usual 20 particles. All right. So let's see how we can compute more properly the fractional charge and statistics of these particles. So what I'm going to do is review a beautiful calculation by Arovas, Schrieffer, and Wilczek. So 2 Nobel Prize winners on this paper. Given that there were 2 Nobel Prize winners on the paper, it's a little bit surprising that they ballsed up the calculation completely. It's absolutely wrong, apart from the answer, which is right. So I guess that really makes a genius. So I'll explain how to do the answer correctly. The right calculation was pointed out by Michael Stone a year or 2 later. So I'll do the correct calculation, and I'll point out where Arovas and Schrieffer made a pretty obvious mistake. But the basic ideas of what I'm about to do are due to Arovas, Schrieffer, and Wilczek, and I think that's the essence. It's just having the idea of how you actually compute these things. So let me tell you the ideas, and then we'll do the calculation. So let's first think about the fractional charge. So the idea is the following. This is your quantum Hall disk. So this is the constant density disk. And then there's some quasi-hole here. And the idea is that we write down this wave function for the quasi-hole. It depends on this parameter eta, which determines the position. And then we're going to adiabatically move this quasi-hole in the circle. Okay, so we're going to take this and move it in the circle. What happens if you do that? Well, we spent a long time, a couple of lectures ago, thinking about baryons. So So when you take a wave function and you move a parameter in a circle, you pick up a Berry phase. So we compute the Berry phase.
So the quasi-call is a gapped object, and you need that to make this construction.
You need a gap. So if you work with these toy wave functions, it has a gap. You need two things actually. You need a toy wave function, and you need a confining potential which sort of squeezes everything. Then you have a gap.
Can I ask in that context something I've been meaning to ask you, which is it's often said that the quantum Hall state is incompressible.
That's right. Yes.
Right? And is that tied to there being a gap?
That's the same statement as there being a gap. Yeah. And if we've done these toy wave functions, we just see explicitly this is the lower state and this is the
Actually, what is that bit about the confining thing? I missed it. Earlier, you took this wave function and you computed what radius it would need to cancel that background.
That's right. Yeah.
Now, with the quasi-hole, if I repeated that calculation, I get
it swells a little bit. Yes. So the statement about the confining thing is if you work with these toy Hamiltonians that are called pseudo potentials, they actually have zero. They're not gapped Hamiltonian. The Laughlin wave function is a ground state, but the quasi-hole has exactly the same energy as the Laughlin wave function. And the way you distinguish between them is the Laughlin wave function is the most compact state you can have. So you write down those pseudo potentials plus some harmonic trap.
So this swelling up is crucial to give it a gap then.
Okay, so move the hole and compute the Berry phase. The Berry phase is some two-dimensional gauge connection, where it's the wave function of the hole. You differentiate with respect to the parameter eta, which is varying, overlap the wave function of the hole. And as we've seen, the Berry phase is eta minus I. That the wave function picks up is the usual variance. But now we compare to what we would expect, because this, of course, is a system with a magnetic field going through it. And as this particle moves around, it's going to pick up the Aharonov-Bohm phase. So you compare this to the Aharonov-Bohm phase. For a particle charge E star. In other words, that means you write the phase gamma as the charge of the particle times the flux through this area, which is just the original magnetic field times the area divided by h. So the calculation is you compute the Berry phase for that Laughlin state. You then compare it to the expected Aharonov-Bohm phase, and from that you extract the charge. Okay, it's very clever. All right. The other thing you can compute is fractional statistics. Which
sorry to be so dumb, but this Berry, the Berry connection is not the magnetic field, right?
No, it's always this auxiliary artificial. And to get the statistics, for example, you might ask, is this hole a boson or a fermi? Well, you can do the same kind of thing. You hook up a system where there's one hole sitting on the origin and another hole sitting here, and you move one hole all the way around another. So 2 quasi-holes. And now you can compute the Berry phase. E to the I gamma. And there'll be 2 contributions. So there's the Aharonov-Bohm phase. Boom. That's the bit we already computed. But now there's going to be an extra contribution, which is due to the statistical phase of this moving around this. So the extra contribution is going to be 2 pi times some parameter alpha, and alpha is the thing we want to compute. So for example, suppose these objects were bosons. If it was a boson, we know that when you exchange... Let me do fermions first. If they were fermions, you know that when you exchange two particles, you pick up a minus sign. Which means that when you rotate one particle around another, you get a plus sign, but this should know that you had a minus sign along the way. So alpha equals 1 would be for a fermion. Okay? Because then the e to the I pi alpha, which was after halfway round, would give the minus 1 from it. Or alpha equals 0 or 2 would be for a fermion. Okay? So let's figure out what these things are. Alright, so that's the basic idea. We're going to write down these quasi-Hall wave functions, compute the Berry phase, and from this extract the physics that we want. What's the charge response to these things? Questions? Should we do the calculation? We'll do it correctly. Okay, so how to compute the Berry phase? Alright, so the quasi-Hall states in general, and this, I'm going to call them eta, and these are going to be the states that have an arbitrary number of quasi-Halls, 1, 2, 3. And strictly speaking, this is the quasi-Hall states in the coordinate representation, so I should take the states and overlaps with the z's. So these are just the quasi-Hall wave functions we have. M is the number of quasi-Halls, N is the number of electrons. So now we have one of these factors for every quasi-Hall. All right. The mistake that Aravash, Schrieffer, and Wilczek made was that they worked with this state eta. But eta is not normalized. And whenever you compute Berry phase, you've got to work with the normalized wave function, not the unnormalized. By the way, they got the right answer. I have no idea why the answer works out right if you work with the unnormalized. Usually you get completely the wrong answer for Berry phase. So it would be nice to understand actually why they get the right answer even though they did the wrong. I don't understand. Okay, so we should work with the normalized state. So the normalized state, we're going to write the normalization factor as 1 over the square root of capital Z. So that's a capital Z, and of course shouldn't be confused with the little z, which are the coordinates. It's capital Z for partition function. Where this thing that I call capital Z is the product with little z's exponential sum of I less than j log I minus j squared plus m sum all right. This is, I call it Z because it's like the kind of things we thought about with the plasma analogy, but now it's almost like the partition function with an impurity. And as we'll see, it's not quite. And the way in which it's not quite will make clear. But that's the basic idea. This is a little like the partition function we saw in the plasma analogy. All right. So we need to compute the Berry phase for this. So there's going to be two contributions. What we're going to do is think about the Berry phase as you vary with respect to eta, the holomorphic parameter, and with respect to eta bar, the anti-holomorphic. Okay? Now the reason that's useful is because this only depends on eta in a holomorphic fashion. And this is where the dependence on eta bar comes from. So if you have a holomorphic path of the Berry phase, so you differentiate the state with respect to eta, the holomorphic parameter. This is writing psi in terms of eta and whatever the square root of z. But now this term, you can rewrite in terms of z, because z is the same thing as eta bar. Oh, sorry, it's the same thing as eta overlapped. If I differentiate with respect to eta, this doesn't depend on eta, this only depends on eta bar. And this depends on eta. Is there a question? Okay, this is because the original whole wave function depends holomorphically on eta. And the original whole wave function is the ket, which means the ket depends on eta, but not on eta bar, and the bra depends on eta bar, but not on eta. Right? So this means that this holomorphic part of the wave function you can write in terms of the log of the partition function with respect to eta. And the anti-holomorphic part you can also write as the log with a plus sign instead of a plus sign. Alright, so what we have to do is differentiate this thing I've called the partition function, which is the way that I just rubbed off, with respect to eta and eta.
Sorry, I missed something. So the first term is by itself of the form I over 2
Factor of 2, is it?
Then minus sign.
Factor of 2, yeah. Minus I by 2.
Okay, I over 2. Is that I over what?
That's not over 2.
2, right. So doesn't that just come from the...
No, this is a plus.
Oh, so that's okay, good. Excellent, thank you.
And here you don't get the second term, you just get the first term.
Okay, thank you.
Alright, so we've got to differentiate this partition function, or the log of the partition function. But as we've seen, this partition function is never something we're going to be able to calculate. It's this horrible integral. So we're going to have to use a little bit of intuition about what's going on.
David, I'll just say something. I've got a feeling I said this at the time, and I can't remember if you had anything to say about it, but if you ignore the normalization, isn't it just a statement that you're moving eta around on circles in all of these problems? So the normalization never depends on eta, because it's only the modulus of eta that matters by rotational symmetry.
Oh, maybe that's the reason. Yeah.
I can't remember if I said that at the time, but that seemed like the reason why it might drop out, because anything is... it doesn't change as you move eta as normalization.
Yeah, Carl pointed out that the calculation they do is just moving it on a circle. And if you move it on a circle rather than a random thing,
then it's fine.
Maybe that's a nice answer.
Well, is it true that the normalization won't change if...
It's just rotational symmetry. Is the
normalization with a mod eta square.
Mod eta square.
Yeah, on the phase of eta. Good.
I see. So then what was the stone paper then?
The stone paper is doing this calculation I'm doing here, which is a more general calculation. We'll see that we'll get results for this and this in general, which are important results. You can match them with conditionalogical formulas if you're so inclined. Okay, so let's look at the plasma analogy. And we're going to think of... So So we'll compute this using the plasma analogy. With the holes appearing as impurities. So they're impurities because these are not dynamical. The positions of the holes are something which is fixed and under our control. With charge as opposed to the electrons, which were mobile particles in the plasma with charge minus. So let's see why this is relevant. Firstly, let me just write down the energy for a bunch of mobile electrons with charge minus n interacting with some impurities of charge plus. So what would the energy of such a plasma be? So there's a bunch of terms. There's the term with the Coulomb energy, which is the force between the particles. And then there's the term which is the force between the particles and the impurities. And then there's the term which is the energy due to the interaction of the impurities amongst themselves. And then there's the term which are the electrons interacting with this constant background charge. And then there's the terms which are the impurities interacting with this constant background charge.
Is that right? I thought the impurities didn't.
They're not dynamical, but this is just the energy for the plasma with the electrons moving with the impurities. And the energy surely has this term.
Because the wave function doesn't have that.
No. So at the moment, let's just back away from the quantum Hall story and say, what is the energy of plasma? And it's going to be the difference between these terms and the wave function that's the key part of the story. Okay, so this is the energy for a plasma, a bunch of electrons moving with these impurities stuck in positions.
You take one of these data as special, which you are going to move in.
Yeah, I'll move each one eventually. But this is going to be a more general calculation, or I could be moving all of them at the same time if I want to compute the variables. Okay, so the plasma partition function is the integral over the electron coordinates e to the minus beta times u, which is, as Sandy pointed out, isn't quite the z that we had before, because this term are different. They depend only on etas and not on z's. So we should write this as the exponential of minus 1 over m, sum over I is less than j, I minus e to j squared. Okay, I'm not quite sure I got minus up right there. May have screwed up.
So now you put in the beta, the temperature.
And now, that's right, and now beta is given by the 2 over m that we had before. Okay.
So z is the partition function with the impurity. So the cross term z minus eta is included.
Yeah. So the capital Z is the thing that you get from wave function, mod wave function squared.
Okay.
Yeah.
Takes
And it's
care of
not
it.
quite the partition function for a plasma because it didn't include the interactions between the impurities themselves, just the electrons to the impurities. Okay. Is this So now comes the key step of the argument. I can't compute this anymore than I can compute you anything else. However, we know what a plasma does. If I stick an impurity here, then what will happen is the electrons will gather around and will screen it. So you'll get some screening from it. And if there's another impurity here, the electrons will gather around and screen it. And as long as the distance between those two impurities is big enough, they won't know about each other. As long as it's bigger than the divide screening. Which means that things like the free energy in this plasma don't know about the positions of impurities. They're completely screened. Which means that this object here is independent of eta. Because the log of this is the partition function for the plasma, the log of it is the free energy, it doesn't depend on eta. So the key physics is screening. Now we look at screening. So the free energy of the plasma independent of the whole positions, at least when they're well separated. Which means miraculously we figured out how the modulus of the wave function depends on eta, because this is just a constant. So this means we can write Z is eta j minus 1 over 2n where C is just a constant. It's very, very complex.
So just to understand, so you introduce in the plasma impurities and you allow them to move around as well. Right?
No, they're fixed. They're fixed. But they give an energy cost to the plasma, which you have to
give an energy cost. Okay. And then the claim is with that energy cost included, the plasma adjusts itself so that the final free energy doesn't depend on that location. Yes. Had they not had that energy cost included?
It's also worth saying, now it's crucial we're in the liquid phase, because you don't get screening if this is in the solid. So you really needed to know this input from numerics, that this temperature is the plasma ready. It's beautiful. It's really very good. Okay, so now it's just two lines of algebra. What do we have? We have that we can now compute the very phase as you vary any of the parameters. So I'll compute the very phase as you vary ith parameter holomorphically, and then as you vary the ith parameter anti-holomorphically. And you just differentiate. Remember, the very phase was a log of z differentiated. You just plug that in, and you get the following results.
Just to clarify, so when you say liquid, you're all along using liquid or gas in that sense? Liquid and...
Yeah, you can show that the particles are close together, so it's really a liquid as opposed to a gas. Not that there's a good order parameter to distinguish them, but it's more like that. All right, so these are the final answers for the very phase as you move Aussie holes around.
This also works for just calculating the charge, right?
Yeah.
If I just have one eta.
The charge using the very phase, or the charge just by thinking about screening?
The charge using this, I don't know.
Yeah, I'll do it now. Yeah.
So in that case, there's only one eta there?
Yes, exactly. So let's see how to do those two calculations just to finish off. There's a fractional charge. And in that case, you only get the second term. So remember, the fractional charge is where you take just one quasi-hole and move it in the circle. And you can very easily compute the very phase. It's the sum of holomorphic A by d eta plus anti-holomorphic A d eta bar. And if you do it, this m here is the thing that is crucial. And this is the Aronoff-Bohm phase precisely for a particle of the over m's. If you want to compute fractional statistics, or let me just say statistics, meaning whether they're bosons or fermions, then it's this term here that's important. But again, it's a very easy contour integral to do. You just get a hole basically from one eta 1 going around position eta 2. Yes?
When you wrote the Boston partition function, you already assumed the charge is 1 by m, right? Because like the charge is of the impurity is 1 and the charge of the electron was m.
Good. So let me see. I assumed. No. The question is the following: can I? It's the same as before. I'll take the wave function. I compute the norm squared of the wave function. Can I interpret that in terms of some statistical mechanics?
Yeah. So,
but I didn't assume anything because the z minus eta term came with a specific normalization.
no, but if you look at the partition function, the charge of the impurity is 1 there, right? And the charge of the
Oh, it is, but I didn't assume it had to be that.
yeah, from that, it's obvious that the fractional charge should be
in some sense, yeah. Well, what you're saying is by looking at the plasma analogy, you could see already that this charge is going to be an X. But that's the same kind of level of the argument I gave originally. Of, well, if you put n of them together, it's
okay.
charge 1. So this I think is a much stronger argument. So if you do fractional statistics, or if you do statistics, I won't do the calculation, but it's just one line. It's very easy to do. You get the Aharonov-Bohm phase. So this is the very phase. Aharonov-Bohm plus e to the 2 pi I over n.
You mean gamma is equal to Aharonov?
Well, gamma is just write it down. It's equal to this e to the I over n bar. But it's clear, this term comes from this piece, and the other term comes from this piece.
Well, actually saying that plus should be a times.
Yeah. So it's a phase that is
This should continue.
yeah.
That's what it is. Good, thank you. Kiddo.
I didn't understand where the eta bar came from in the calculation of I gamma.
Where this comes
Second
from?
term, yes.
This,
I thought we were doing d by d eta or...
No, so e to the I gamma is e to the minus I in vector notation. It's this. So this is just going from vector notation to complex notation.
Okay. So you need both.
You need both. So what do we find? We find that these objects aren't fermions or bosons. These objects are something completely new. So if you exchange two holes, so this is the phase that you get if you take one hole all the way around another one, which means if you exchange, you're going to get half that phase. So if you exchange, you get e to the pi by So these quasi-holes not proton zombies or they're not photons. So we see that these objects which are roaming around in the quantum Hall fluid are very, very surprising. They have a fraction of a charge of an electron, and they have, in some sense, a fraction of the statistics of an electron as well. So they're really astonishing new objects in theoretical physics. It's worth saying that there are now very compelling experiments that the charge is EOA. Various shock noise experiments. You can really measure the charge carriers. It's much harder to cook up experiments that measure directly the phase. So there are a bunch that claim to see it. I haven't looked at them in detail, but they're not uncontroversial. There are various people that argue about the interpretation of these experiments. So I think it's still an open problem to try and come up with a watertight experiment that shows that they really have this phase. But it's such an integral part of the theory. They really have to have it. They really have to.
So when you wrote the whole you said that etas are not dynamic, right?
Yes.
So what do you mean by they move around?
Ah, good. So it's a good question. So I just wrote down the wave function where they were at some place. But in principle, if you were to, let me say it this way. So suppose I was to add an electric field onto my sample. So I was to deform my Hamiltonian in some way. And there was before that, the quasi-hole sat there. Then in the presence of the electric field, the new ground state that state will evolve, and that quasi-hole will move as if it's some independent particle. That's what best way to think is.
Already in the harmonic trap, if you actually look at the actual ground state as it evolves according to the Schrödinger equation, that quasi-hole moves in circles, so you kind of,
if you really
kind of accidentally has some dynamics.
It goes around.
David, can I ask you, I understand your fractional statistics definition, but the way you defined your charge here was sort of more in comparison with had you a charge and you picked up a phase because of the ambient magnetic flux by comparing the phase you're picking up here with that. Right? But there could be another definition of charge which is operationally more closely linked to how the system behaves in response to an electric field or something.
Yeah. I mean, it's probably that definition which is measured in experiments, I suppose.
And that is the same as this.
Yeah, I don't quite know how to...
The reason I'm asking is, it's a bit counterintuitive. I mean, I'm trying to understand this because, of course, anytime from the external world you introduce a charge, it will always be quantized in the usual units.
Of course, right. So what's really going on is that m of these particles can wander at once independently around in this cycle.
And so that's what happens. In response, you need m of them to move around. So in a sense, you can't excite one of them through an experiment where you got external means into the world.
Because at the end of the day, you'd be surrounded by, it's called some surface, some Gaussian surface, and you measure. You have to have an integral number of charges.
Right. That's what I'm wondering.
You can't violate the laws of physics. Yeah, so there have to be an m of them that move around, but they can move around completely
independently. And that's what the shock noise or whatever
It's a fluctuation, yeah. So that's
it's a fluctuation that I see.
It's the fact that you are creating them, that's what will be kept. So total number will always be in response m of them.
So, but is there another way to? Is it possible in a way to measure the? I mean, is there something else which measures the fractionality in a more direct way? I mean, it's always that it's m independent things adding up to integer charges. I guess must be.
I'm not sure you see that.
But can you see the Aharonov phase which is fractional in some direct way? Like you do the Aharonov experiment inside the quantum Hall system.
Yeah,
I don't think you have range control.
You don't
Not that kind, but you do this kind of interference experiments where you have like two sets of things with a barrier and then you look at how charges go, and
this is
ultimately in the lead you will always pick up the full electron, but then you can look at the interference of various things, and
this is supposed to measure this.
Yeah, that's
I don't know the full story, but people will argue that there's.
So the fractional statistics only shows up in the value phase. Does not show up in any other measurable quantity. You can say statistics is not.
So you you can, in principle, set up experiments where you get these things to interfere with each other. So it's something like, the original Arrow-Probe experiment was to send things through a flux and see changes in interference. So you could, in principle, do something like that to measure this. I'm just saying the experiment hasn't been, to my knowledge, clearly done.
The statistics much sure. I imagine when you start doing thermodynamics, right? Because a Fermi gas is different from a boson.
Yeah, so no, the virial coefficients in the equation of state differ from this, and interpolate from Bose to Fermi.
Right.
So if you heat up a quantum Wald sample, it's no longer a quantum Wald sample. If you heat up a quantum Wald sample, it's no longer a quantum Wald sample. So you have to try and find some window, right, where you don't destroy the state. But you have enough of these moving around.
Right.
I don't think that's
not possible. Okay. Sorry, I thought maybe you could, and then you start seeing the anionic gas.
Maybe people make cold atom systems that cook up these things, like various proposals. So maybe in the future it's worth mentioning one argument before we finish. We had this Laughlin argument for the quantization of the integer quantum Hall effect, which was a ring, an annulus like this with a flux through the middle. You increase the flux by 1. If a single particle moves, that's quantum Hall conductivity 1. Okay. If you want a fractional quantum Hall conductivity, you need to have a fractional electron to move from one end to the other. But miraculously, we've got a fractional of an electron. So what happens in that setup is when you crank the flux by 1 through the middle, it's precisely 1 quasion, which moves from one end to the other. So how you can get fractional quantum Hall states from.
So is the screening argument the only place where the phase is important, whether it's liquid or solid, or will it become crucial for some other arguments?
Kedar seemed to be saying it was crucial for conductivity itself, although given that, I'm not sure about that. But it's certainly crucial for
the screening,
for the statistics. You need the screening. By the way, if you on Mondays, this is minor advertisement for Carl and my work. On Monday, I'm going to give a seminar, and one of the things we'll do is show how you can compute this without invoking plasma analogy, without invoking the need for screening. Just actually do the calculation.
So fermionic statistics means that no two particles can occupy same state.
Yeah.
So here it means that m particles can occupy one same state.
No. In fact, it's if you think about
fractional.
If you were to really try and write down a wave function for these objects involving this, to J, these are complex numbers. So let's suppose we write down a wave function for the ground state. So it still vanishes as two come together. But now the wave function is not a single value. So as the wave function has branch. So as you do one around the other, you'll pick up the phase, but at the expense of having a non-single value wave function for the object you're trying to. So things get complicated when you try to write down wave functions for these things.
So basic Pauli repulsion would occur for anything other than bosons. That's not the whole story. You get to see the branch pattern.
All right, we're good. So next week we'll talk about topological order, which is the last sort of key bit of physics hidden in this, and then we'll go on and talk about Jane's work generalizing to the other fractions that are secret.